welcome to next lecture of strength of material. Now topic is complex stresses. In the introduction class, we studied the Uniaxial stress and uh, what which produce either tensile stress or compressive stress. Okay, but this tensile or compressive stress also produces uh, shear stress or tensile or compressive stress in the plane within the body. Okay, so we in this class we will find out the effect of these stresses, either uniaxial stress, uniaxial stress in one direction, or biaxial stress, or it means stress in two directions. Okay, and effect of shear stress acting on an object. Okay, so uh, we start with the force. Okay, we know that a single force we know that a single force can be a single force can be balanced by two component forces acting perpendicular to each other. Okay, this we have studied in applied mechanics. Okay, like like this force acting on a body can be replaced by this Pn and this Ps. Okay, or we can say that this force P can be balanced by Pn and Ps. Okay, two different forces which are perpendicular to each other. Okay, this is the basic idea in this chapter. Okay, and it will be used to find out the stresses in different planes. Okay, so we take the simple case of uniaxial stress. It means the stress acting in one direction. That is sigma x. Okay, we are not taking the forces, we are exactly taking the stresses in the one direction, sigma x. This is the x direction, this is the y direction. Okay, so this stress can also be written as sigma xx. First letter represents the direction and second letter represents the plane. How the second letter represents plane? This is the plane on which the stress is acting. Okay, okay. This plane is YZ plane. Okay, YZ plane. If we skip Y and Z, then there will be only X. So this can also be written as sigma XX. Okay, and we will discuss it further. Okay, in this system, as shown in figure, sigma x is a uniaxial stress. Okay, when this sigma x is multiplied by the cross section area of this, it will give force. Okay, so this is the force P force. PC is acting on plane BC. P force, and here the force is also PC. P. Okay, so we have to find out the stress at plane AC. Okay, now if we replace this P by Pn and Ps, we can replace, okay, then divide this Pn and Ps by their respective area, we can find out the stress. Okay, so in find out stress on this plane, the Pn will generate normal stress. Normal stress it can be either tensile stress or compressive stress, and PS will generate shear stress. It can be either sorry, it is shear. It can be clockwise or anti-clockwise. Okay. Okay. So first case is uniaxial stress. Now consider a block ABCD with the sigma x stress acting on this, and the thickness of this ABCD block perpendicular to the paper is 1 mm. Okay, as shown in figure. Hmm. The plane AC, this is plane AB, okay, and this is plane BC, and this is plane AC, is at angle theta to the plane AB. Okay, where we are required to find out the stress. Now we assume that sigma theta is the normal stress acting on plane AC, and tau theta is the shear stress acting on plane AC, and we'll find out the value of these stresses. Okay. Now the force on the plane BC is, as we can replace, we can also uh, we can also say that sigma x is replaced by sigma theta and tau theta, and this sigma x we will say this sigma x is replaced by sigma tau theta, and this sigma x remains same, and this sigma x and this sigma x is balanced by sigma theta and tau theta. Okay. Now if we multiply sigma x by area, what is area? Area is intensile stress is intensile or compressive stress is perpendicular to the paper. It means the area is sigma x BC, and thickness of the object which is 1 sigma x sigma x sigma x BC into 1. Okay. And now the area for this sigma theta is, the sigma theta will be AC, thickness of AC is 1. Okay, because the thickness of the block is 1. Okay, so the area for this sigma theta is perpendicular to the sigma theta because it is tensile or compressive stress or normal stress. So sigma theta AC into 1, and area for this tau theta is sigma theta into AC into 1, because in shear stress the area is parallel to the applied stress, so sigma theta into AC into 1. Okay, so this is the force diagram for. Now we replace it ABC as ABC block as a point. Okay, then then we can obtain equilibrium diagram. So sigma x BC one will be acting in a positive direction, and sigma theta AC one will be acting at an angle theta in y direction, and tau theta AC into one will be acting at a theta in negative x direction. Now, if we rotate the whole diagram by an angle theta, then this sigma theta AC will come here, okay, and sigma x BC will come here, okay, and tau theta AC will come here. Now it is easy to find out sigma theta, theta, and tau theta, because they are sigma theta is in vertical component and tau theta is in horizontal component. Okay. Now resolving vertically, the vertical part of the sigma theta is sigma theta AC one. It has only the vertical part, and the vertical component of sigma x BC one is sigma x BC sine theta. So this is vertical upward, this is vertical downward. So we can balance this sigma theta AC into 1 because of sigma x BC into 1 is sine theta, and this AC comes here, so BC by AC From this diagram, BC is perpendicular and AC is hypotenuse. So it is sine theta. BC by AC is sine theta. BC by AC is sine theta, and this is sine theta. So sigma theta is sigma x sine square theta. Now we know that sine square theta is 1 minus cos square theta divided by 2. Uh, then it is sigma x. So we can find out sigma formula for sigma x. Sigma theta is equal to sigma x by 2 minus sigma x by 2 cos 2 theta. This is equation number 1. Okay, this we have obtained from by resolving vertically. Now, if we resolve it horizontally, we can find out tau theta. Now it is tau theta. Horizontal part of tau theta is same. That is tau theta AC1, and horizontal part of sigma x BC1 is sigma x BC cos theta. Okay. So this is tau theta AC1, sigma x BC1 cos theta. So this AC will come here, and again BC by AC is sin theta, and sigma x sin theta, it will become sigma x sin theta cos theta, and we know that 2 sin theta cos theta is sin 2 theta, so we can write sigma theta is equal to sigma x sin theta by 2. Okay, so this is the second equation. Now for uniaxial stress, we can cram these two formula. Okay, if we want to find out, the stress at an angle theta to the direction of sigma x. Okay, to the direction of sigma x. This is the direction of sigma x. Okay, and we can say the plane of AB, plane AB, to the plane of AB. Okay, this is the direction of sigma x, and plane AB is same thing. Okay, if in the question it can be asked that find the stress in the direction of, find the stress at an angle theta into the direction of sigma x, or to the, or at an angle theta to the plane AB. Okay. Okay, so these are the two formulas to find out sigma theta and tau theta at an angle theta to the direction of sigma x. Okay, so if we put theta is equal to 0, okay, then it is plane AB. Okay, this is theta is 0. If theta is 0, if theta is 0, it is plane AB. Okay, so to find out the stresses at plane AB, we put the theta as 0. Then it is, then sigma theta is 0, because here if we put sigma tau theta is equal to 0, this will be 1. Okay, so sigma x by 2 minus sigma x by 2 is 0. So sigma theta is 0. Now if we put in this equation sine 0, so this is tau theta is 0. So there is no stress acting on plane AB. Okay. Now if we put theta is equal to 90, then it is plane BC. It is plane BC. Plane BC. Okay. So at plane BC, the stress acting is sigma x. Stress acting is sigma x. Okay. And so sigma theta is sigma x, and if we put here in second equation theta is equal to 90, then tau theta will be 0. Tau theta will be 0, or we can say sin 180 is 0. So there is no shear stress acting on this plane BC, which is the case. So it is the case of, as it is the case of uniaxial stress. Okay, so theta is 0 at plane BC, and sorry, theta is 90 if you plane the plane BC, and sigma theta is sigma x and tau theta is 0. So when theta is 0 and 90, the shear stress acting on these planes are is 0. Okay. At this plane, theta is also 0. At this plane, theta is also 0. Okay. So, so the planes where there is no shear stress are called principal planes. Okay. So these AB and BC in this case are principal planes. Okay. Okay, so principal planes are defined as the planes where the shear stress is zero. Principal stresses are the normal stresses acting on plane. Okay, the principal we have noted down the principal planes. The principal planes are defined by the absence of shear stress. So, but it doesn't mean no stress is acting on the principal plane. Normal stresses are always acting on the principal planes. Okay, so the normal stresses acting on the principal planes are called principal stresses. Okay, okay, are principal stresses. Okay, principal stresses are the normal stresses acting on the plane. Or the bare stress and is zero. Now, if we put theta is equal to 45 in this case, okay, theta is equal to 45 in this case, then the sigma theta will be, okay, this is cos 90, uh, cos 90 will be 0 and it will be sigma x by 2, okay, cos 90 0 and this will be sigma x by sigma theta will be sigma x by 2, and if we put 135 degree, then it is again cos is negative in second quadrant, okay, cos is negative in second quadrant, but here it will be 270 and 270 0 sigma x by 2. So again the add theta, sigma theta at theta is equal to 135, sigma theta is sigma x by 2, and at theta is equal to 45 degree, sigma theta will be sigma x by 2. Okay. Now in the shear stress expression, if we put theta is equal to 45 degree, it will be sin 90 is 1. Okay, and tau theta will be sigma x by 2. Okay, sigma x by 2. Okay, this is the, and again if we put theta is equal to 135 degree, sin 130 sin 270 degree is minus 1, so it will be sigma theta, it will be equal to sigma x by 2 and with sin sin value minus. Okay, here sorry, to add 45 degree and add 135 degree, the value of shear stress is maximum and minimum. Okay, we can say that if the clockwise shear stress is acting on this plane, then it is sigma x by, then it is positive, and if anti-clockwise stress is acting on this plane, then it is negative. Uh, then it is negative. Okay, so this is sigma x by 2 maximum value, and this sigma x by 2 with anti-clockwise direction is minimum value. Okay, so these are the planes of maximum and minimum shear stress, maximum minimum shear stress plane with their sign. Okay, so we in this we, we saw that the shear normal stress is maximum at plane BC. Enormous stress is maximum at plane BC and zero at plane AB. So this is the maximum principal stress, and the zero is the minimum principal stress. And the shear stress is maximum at an angle 45 degree to the plane of maximum normal stress or the principal plane. Okay, and the 35 degree is the at 135 degree the shear stress is minimum at the shear stress is minimum. Okay, so this is the plane of minimum principal minimum shear stress. So we can say this is true for all the cases we will discuss, that we will discuss later. Okay, so it means, so the shear stress Maximum shear stress always act at 45 degree to the 45 degree to the principal plane. Okay, from above, the shear stress attains maximum magnitude at a plane 35 45 degree and 135 degree to the principal plane, or it can be said the plane of maximum shear stress is always at 45 degree to the plane of maximum normal stress or principal plane. Okay. Now it may be noted that at principal or maximum normal stress, the plane, normal stress plane or principal plane, we can say, the shear stress is zero. Okay, that is the definition of principal plane. Okay, where as at maximum shear stress, the plane, the normal stress is not zero. It is equal to sigma x2. Okay, that is. So at principal plane, the shear stress is zero, but at and normal stress can be maximum or minimum, but at maximum shear stress plane, it is not necessary to have zero normal stress. Okay, this is the important point. At maximum shear stress plane, it is not necessary to have zero normal stress. Okay, so the thing that so in this case, sigma 1 is the maximum principal stress, sigma and minimum principal stress 0, maximum shear stress sigma x by 2. And we saw that tau max is equal to this minus this by 2, sigma 1 minus sigma 2 by 2, this is sigma x by 2. Okay, sigma tau max is equal to sigma 1 minus sigma 2 by 2. This is the in all the cases. Okay. Okay, this is the case of uniaxial stress. It means the stress acting in only one direction, that is in x direction. Now, next case is of biaxial stress. Okay, biaxial stress, the stress acting in two directions, in x direction and in y direction. So this is a sigma x stress acting in x direction, and this sigma y stress acting in y direction. It can be repeated as sigma xx. It can be repeated as sigma yy. Okay. Okay, in the similar manner, now this sigma x and this sigma y can be replaced by sigma theta and tau theta. So sigma theta and tau theta. Now, if we multiply them with their respective area, we can find out forces. So it will be sigma x BC into 1. Okay, because thickness of the block is taken as 1, and this is sigma y into AB into 1, and this is sigma theta AC into 1, and this is tau theta AC into 1. Okay, so this is the force diagram. Now equilibrium diagram, sigma x BC into 1, and this tau sigma theta AC into 1, and this is tau theta AC into 1, this is sigma y AB into 1. Okay, so this is equilibrium diagram. Now equilibrium, if the equilibrium diagram is represented by angle theta, then this sigma theta AC into 1, tau theta AC into 1, and it will be rotated by sigma x BC into 1. This will come at angle theta, this will also come at angle theta, this will be horizontal, and this will be vertical. Now the purpose of the rotation is to bring the sigma theta and tau theta as vertical and horizontal part. Okay, so that we can resolve all the forces and find out sigma theta and tau theta. Okay, so uh, resolving vertically, vertically it will be sigma theta. Vertical component will carry sigma theta AC into 1, sigma y AB cos theta, and sigma x BC sin theta. Okay, balancing these are in downward direction, this is in upward direction. Okay, now again following the same procedure, divided by AC, BC by AC, and this is AB by AC, BC by AC is sin theta, AB by AC is cos theta, and this will be sin square theta, this will be cos square theta. Okay. Now sin square theta can be written as 1 minus cos theta by 2, and cos square theta can be written as 1 plus cos theta by 2, and this sigma x plus sigma y by 2, and this will be sigma y plus k and sigma x minus y by 2 cos theta. This is the expression for sigma theta. Now resolving horizontally. Okay, resolving horizontally, horizontal component is tau theta AC 1 sigma by AB sin theta sigma x BC cos theta. Okay, tau theta AC into 1 sigma x BC into 1 cos theta sigma by AB into sin theta. BC by AC is sin theta and AB by AC is cos theta. Okay, so sigma x minus sigma y, you can take common sin theta cos theta, and sin theta cos theta is sin theta by 2. Then this is sigma x minus sigma y by 2 sin 2 theta. Okay, now putting in third and fourth different boundary conditions, if we put theta is equal to 0 here, okay, then theta is equal to 0 here, it will be 1, okay, and sigma x by 2 and sigma x by 2 will cancel out, and it will be sigma y. Okay, if theta is 0, it means it is plane AB, and sigma y is, if theta is 0, then it means it's plane AB, and sigma y is acting on this plane. Okay, if theta is 90, then it is plane BC, and sigma x is acting on this plane. Okay, and there is no shear stress acting on this plane. If we put theta is equal to 0, then it will be sigma y. If we put theta is equal to 90, it will be 1, and it will be 90, and it becomes out as, sorry, it will be 180, and it will be negative. Negative means only sigma x will be left. Okay, so if we put here theta is equal to 0, sin 0 will be 0, and if we put theta is equal to 0 or theta is equal to 90, it will be 180. So then this will be tau theta, it will be 0 in both the cases. So in this case, theta is equal, at theta is equal to 0 and theta is equal to 90, there is no shear stress. It means these are principal planes. So AB and ABC, AB and BC are AB and BC are principal plane. Okay, AB and BC are principal plane, and the stresses acting on this plane are principal stresses. So sigma x and sigma y are principal stresses. One of them can be the maximum principal stress, and another is minimum principal stress. Now, if we put theta is equal to 45 degrees here, we put theta is equal to 45 degrees, it will be cos 90. Cos 90 is 0, and it will be sigma x plus sigma y by 2. Okay. Okay. Sigma theta will be sigma x plus sigma y by 2. Similarly, if we put theta is equal to 135 degrees, sigma theta will be sigma x plus sigma y by 2. Okay. And in this expression, if we put theta is equal to 45 degree, it will be 90 degree. Okay, sin 90 degree, and tau theta will be sigma x minus sigma y by 2. And similarly, tau theta at 135 degree will be minus sigma x minus y sigma y divided by 2. Okay, so it is at theta is equal to 45 degree and 135 degree plane, there are maximum shear stress, or these are the planes of maximum shear stress. And here we also can see that there is no, there is some normal stress also. The value of normal stress is not 0. It can be 0, it cannot be 0. But at principal plane, the shear stress is always 0. That is the definition of principal plane. Okay. Okay. Next topic is complementary shear stress. Okay. What is complementary shear stress? We have studied shear stress. Okay. That is the shear stress is applied by the two parallel forces. Okay. To be multiplied with their area with the area parallel to the forces will become shear stress. But if a shear stress, okay, sigma xy and tau xy is acting, okay, on a body, on a block ABCD, then this, if this sigma xy, okay, sigma xy is in clockwise direction, okay, clockwise direction, and if we multiply this sigma xy by the area, okay, and this tau xy will be by the area AB into 1, then it will become P, and this will also become P, and this is the distance between them. So it will create a moment try to which will tend to rotate it in clockwise direction. Okay, but this is not the case in tenth the rotation of the body is resisted and the formation of the body is considered. So to form body, a opposite shear stress is also acting when a opposite shear stress is when the shear stress in one direction is acting. This opposite shear stress tau yx will provide an anti-clockwise moment, okay, an anti-clockwise moment which will deform the body, okay. If there is free rotation, okay, then there will be no stress, no strain. So to cause stress in the body, a complementary stress has to be considered in every case where the shear stress is active. So this tau yx will tend to rotate the body in anti-clockwise direction, and this tau xy is will tend to rotate in clockwise direction, and because of this opposite rotation, the body will deform. So this tau yx is called complementary shear stress. Okay, okay. So I can read out for you. Let a shear stress tau xy be acting on a plane AB in clockwise direction. If this clockwise stress is considered alone, then it when it when multiplied by the area and distance between them gives a torque which tends to rotate the block in clockwise direction. To perform the a body, clockwise torque has to be balanced by the to deform a body, a clockwise torque has to be balanced by the counterclockwise torque, so which is provided by the complementary shear stress. Okay. So tau yx is the complementary shear stress acting on a plane BC, which tends to rotate the block in counterclockwise direction, hence balances the clockwise rotation. So complementary shear stress will be equal in magnitude to the applied shear stress, but opposite in direction. ठीक है? To the applied stress. Sorry. When shear stress is represented by tau xy. Okay. Now how the representation takes place? Okay. Here I am representing shear stress by tau xy. Okay. As I have already said that this first letter is for direction. This is in x direction. And this first letter is also for direction. This is in x direction. And second letter is for plane. This is the plane of y. Okay. Plane of y, or we can say this x. This is x. Sorry. So this is the plane x z. So this is x and this is z. So x z plane, we will skip x z and then we put y. Okay. So similarly in this is the direction y, and x is for plane. This plane is y z plane. So we will skip y and z and put x. read out. I'm reading out. When the shear stress is represented by tau xy, then the first letter, that is x, represents the direction, and second letter y represents the plane. The plane is xz. Okay, so we can represent three three directional stresses in matrix form. Sigma xx sigma xx is stressed in x direction and on plane yz. Tau xy is stressed in x direction on xz plane, or we can also represent as shear stress x y. Okay, whenever these letters change x and y, then it is shear stress. Okay, whenever the letter remains same, like sigma x x x, sigma y y, and sigma z z, it is normal stress. Okay, and complementary shear stresses are always equal. It means tau xy and tau yx will be equal but opposite in direction. Similarly, tau xz and tau zx will be equal but opposite in direction. Similarly, tau yz and tau zy will be same but opposite direction. Next topic is pure shear. Uh, so we have studied that sigma, whenever a shear stress is acting on a block, complementary shear stress will also act on the other plane, on the perpendicular plane. Okay, so consider a block having this tau xy as shear stress and tau yx as complementary shear stress. Now, due to these stresses, we will find out the stresses on plane AC. Okay. Now, similarly, as in previous article, this tau xy and this tau yx can be replaced by sigma theta and tau theta. Okay, sigma theta and tau theta, and this is tau yx, this tau xy. Okay, now if we multiply with their respective area, then with their respective area. Okay, if we multiply it by with the respective area tau yx bc, tau xy ab, okay, and sigma theta ac 1 and sigma theta ac 1, okay, we can get the force diagram. Okay, now if we if we uh, take all these forces, then it is a and take all these forces and take it as a point, then it will be equilibrium diagram. Okay, now tau yx bc is in upward direction and tau xy ab is in leftward direction. Okay, and this is sigma theta ac 1 and this is tau theta ac 1. To find out sigma theta and tau theta, we will rotate the diagram as we have done in previous articles. Okay, so that the sigma theta becomes vertical and tau theta becomes horizontal. Okay, okay, now this is the equilibrium diagram when rotated by theta. So this is sigma theta AC1, this is tau theta AC1, this is sigma xy AB1, this is tau yx by tau yx AC1. Okay, so, so resolving vertically. So this is vertical and tau xy AB sin theta is also vertical and tau yx BC cos theta is also vertical. Okay, so resolving vertically, we can find out sigma theta AC1 minus tau yx AB1 sin theta, tau yx bc1 cos theta sigma theta tau xy cos theta sin theta minus tau yx sin theta cos theta. So sigma theta is minus tau xy sin 2 theta. This cos theta sin theta is sin 2 theta. 2 cos theta sin theta is sin 2 theta. So this is sin 2 theta. Okay. Because in magnitude tau xy and tau yx are same, we can take it as minus tau xy sin 2 theta. They are equal but opposite. So we have taken the direction. Okay, this is in upward direction. Tau yx is in upward direction. Okay, and sigma xy is in negative x direction. Okay, so we have taken the direction. We now only will take the magnitude. So we can write sigma xy and tau xy are equal. Okay, they are equal. Now resolving horizontally. When we take horizontal direction, this is sigma theta AC. This will be cos theta. This will be again this will be sin theta. Okay, resolving horizontally. Tau theta AC into 1. Tau xy AB cos theta. Tau xy. This is in positive direction. This is in positive direction. This is in negative direction. Okay, so it will be negative here and positive. So again, AB divided by AC, AB by AC is cos theta, and BC by AC is sin theta. So it will be tau xy cos square theta plus tau yx sin square theta. So cos square theta minus sin square theta is cos 2 theta. So it is minus tau xy cos theta because tau xy is equal to tau yx. Okay. Now if we put theta is equal to 0, if we put theta is equal to 0, here sigma theta is equal to 0, okay, then theta, if we put theta is equal to 0, then it is 0, okay, sigma theta is 0, and it means there is no normal stress acting on plane AB. If we put theta is equal to 90, again sigma theta is 0, means there is also no normal stress acting on this plane AB on BC, okay, on plane BC. On plane BC. Okay, so sigma theta is 0 and tau theta is 0. Sigma theta is 0 in plane at plane 0 and 90 degree, and it means the shear stress is acting on this plane are tau xy and minus tau xy. Okay, by putting theta is equal to 0 in the shear stress expression. Okay, so these are the maximum shear stresses and maximum minimum shear stresses. Okay, on that these are the maximum and minimum shear stresses. Why? Because on any other nowhere in the system the shear stress or any shear stress will exceed from these values. Okay, so these are the planes of maximum and minimum shear stress, and these are the values of these are also the values of maximum and minimum shear stress. Okay, so we can see that at the planes of maximum and minimum shear stress, the value of sigma theta is 0. Okay, here in this case, but in the previous cases there is some value of normal stress at the plane of maximum shear stress and at the plane of minimum shear stress plane. Okay, at the plane of minimum shear stress. Okay, hmm. so so we can say there can be normal stress, there cannot be normal stress at the plane of maximum shear stress. Okay, so theta, so 0 and 90 degree AB and BC are the planes of maximum shear stress in this case, and the normal stress is acting on the maximum shear stress plane is 0. So this system, so this system of stress is called pure stress because this is called pure shear stress, pure shear system because in this case where the maximum shear stress are acting, the normal stress is 0. So this is the only case where the normal stress is 0. Okay, at the plane of maximum shear stress. Or we can say in all the cases where the normal stress is 0, okay, at the plane of maximum shear stress, okay, then it is case of pure shear. Okay. Now if we put theta is equal to 45 degree and theta is equal to 35 degree. Okay, we find out sigma theta will be minus tau x by and sigma theta at 35 degree will be tau x by. And tau theta is 0, tau theta is 0 at 45 degree and 135 degree. Okay. But so these as there is no shear stress on this plane, so we can say these are the principal stresses. Okay. So and theta is equal to 135 degree and theta is equal to 45 degree are the planes of are the principal planes. Okay. And sigma x y tau x y and minus tau x y are the magnitudes of maximum and minimum principal stresses. Okay. These planes are represented in the figure. This is the plane AB. Okay, here tau xy and this tau xy is acting. Okay, and in this plane, complementary shear stress tau yx and tau yx is acting. Okay, so at this plane, theta is equal to 45 degree. We have found out that sigma theta is minus tau xy. So at this plane, theta is equal to 45 degree. It is a minus tau xy means it is compressive. Okay, and similarly at this plane the magnitude is tau xy. So this is maximum shear stress. Okay, this is the plane of maximum shear stress. This is the plane of maximum normal stress. This is the plane of minimum normal stress. At this plane, the value of shear stress is 0. Okay, next and last article of this lecture. Now we have studied the uniaxial stress, we have studied the biaxial stress, we have studied the pure stress. Combining all these expressions, okay, uh, combining the expression of biaxial stress and pure shear stress, we can find out the formula for the formula for the normal stress at an angle theta and shear stress at angle theta when the body is subjected to complex stresses, that is uh, biaxial stress plus shear stress. By combining that above 3 and 5, you can write out sigma theta. Okay, similarly combining 4 and 6, we can write out tau theta. Okay, so if we put theta is equal to 0, okay, theta is equal to 0, then we'll find out there will be sigma y, okay, at theta is equal to 0 and shear stress will be tau yx. So these are not the principal plane. Okay, this is not the principal plane because shear stress is acting on this plane. In the previous case, in the biaxial case, the sigma y is only acting on the plane AB. Okay, and sigma x uh, is acting on plane BC. So this is not the these are not the BC and AB are not the principal plane in this case. Okay, so but there exists a principal plane. Okay, So we can find out the principal plane by the definition of the principal plane. The definition of the principal plane is the plane of zero shear stress. So we will put this relation if tau theta is equal to 0 in this case, okay, in this case, and we'll find out the tangent to theta. Okay, we'll find out the angle theta. Or, so angle theta is the angle of the principal plane with the plane AB. Okay, with the plane AB. So once the principal plane are found, we can find out principal stresses. We tangent to theta is here 2xy sigma x minus sigma y. So this is the principal plane angle. Okay. So in the if we put the value of this angle in the expression of normal stress, we can find out principal stress. We can find out principal stress. Now, in the normal stress formula, there are there is cos to theta and sin to theta. If we know tangent to theta, we can find out sin to theta. Okay, taking it as perpendicular. Okay, and this as base. Okay, this is hypotenuse. So sin theta will be 2 tau xy plus minus root sigma x minus sigma y square plus 2 tau xy square. Similarly, cos theta is sigma x minus sigma y divided by plus minus root sigma x minus sigma y square plus 2 tau xy square. Okay, so putting in this equation sigma theta, okay, we can find out this result, uh, the value of sin to theta, sorry, the value of cos theta here and sin theta here. You can solve it. So this is with the base, the LCM is same. Okay. Now it means 1 by 2 LCM is same. So we can find out the formula for normal plus sigma x plus sigma y by 2 plus minus 1 by 2 sigma x minus sigma y square plus 2 tau x y. Okay. So plus is for maximum normal stress, minus is for minimum normal stress. So this is the and maximum shear stress is difference of 2 divided by 2. This is the maximum shear stress. Okay. So from these formulas 9 and 10, we can derive the formula for uniaxial stress also. If we put sigma y and tau x is 0, it is the case of uniaxial stress, then the sigma 1 and sigma 1 will be x and sigma 2 will be 0. And similarly, tau max will be sigma x plus 2. Okay. Now if we put tau xy is equal to 0, then we can find out the expression for biaxial stress. Then tau max will be sigma x minus sigma y by 2, and sigma 1 and sigma 2 are sigma x and sigma y. So tau max will be plus minus tau x. Okay. Thank you.